Hi, today we're going to go over a quick AMC speedrun. Basically, we're just going to try the problems and see if there are some interesting approaches. We're also nearing the AMC, so it's probably something interesting and fun to try. Uh, Let me get get this set again. All right. First question is very simple arithmetic. You would have 3 over 10 here, and then you would have 33 over 10 for this whole part. And then this is 3 plus 10 over 33. And that's 99 plus 10 over 33. So it's 109 over 33. The sum of three numbers is 96. The first number is 6 times the third number, and the third number is 40 less than the second number. So you have x plus 40, and 6x. The absolute value of the difference between... Okay, so you just find what these numbers are. And you can find the difference between the first and second. So it's second one's 47, and this one is 42. So the difference is 5. Which of the 5 rectangles is shaded in the middle? This is, I guess we can just play around with this. So you have these rectangles. Okay, let's suppose we have 1, 6. What would this imply about the other ones? Or actually, let's start with something more extreme. I think the 7 is very special, so we can start. Let's say this is 7 somehow. This is 7 too. Then what else can we deduce about this? Oh well, the 5, 6 is also very special. Oh no. They're a square, so you can just find what the square side length is. My bad. So this is 6 plus 8 plus 30 plus 14 plus 6, and that is 64. So that is 8 squared. So a side length is 8. And so you can, if you have the 7 here, you would get a 1 here, and that would be a 6. 2 could be 4 or something else. So we'll first put down the 6, 5. And now it's between 2, 4, and 2, 3. We see that this is 2, and we see that this is 4. So this has to be 3, right? Yeah. So this is 2, 4, right over here. So this is rectangle B, respectively, B. So yeah. So here we have N18. LCM is 180. GCD is 15. So from this one here, we know that n is a multiple of 15, and 3 does not divide this k. So this is n. And because if you have x, y as an LCM of something, then x divides something. So you have 15k divides 180, and k divides 12. So, but then 3 does not divide k. So k must be equal to 2 or 4 or 1. Right? Yeah, so these are all the possibilities, and you can try them one by one. So if you have 15 here, what would this be? This would be, would this be 120? No, this would be 180, right? This would be 3 times 5 times 6. Oh, it would be 90. Yes, sorry, my bad, 90. So this would be 90. 30 would also give 90. And then if you have a 60 with the 4, you would get 180. Yes. So the answer is 60. So it's 6. All right, this next one, let me get some space. We have the plane, and you have the origin here. And we want to know, basically this is a Manhattan distance, and you want to know the number of points that have distance less than or equal to 20. So it would look something like this. And all the points along these lines, so if you have like a negative 119, 119, so on, they would all be within what we want. So we would just basically want all the points here. One way we could do this is we can separate this into, like, we could separate them into this and then the origin. So like we have 4 of these triangles, and then we have the points that lie on the axes. So the axes, we have total 20, 20, 21. So this is 81 on axes. And for each triangle, we have from 1 to 19. Notice this is 19. And 1 to 19 here. So this would be, well, so here you would have 19. To the very end, you have 1. So it's basically 1 all the way added to 19. That's 190, right? 190. And that would give 760, and that is 841. Right, so now we have the arithmetic mean of 6 numbers is equal to a value in the data set. Okay, so basically we're considering their sum, which is 20, plus x over 6 is equal to something in the data set. So we can just case work one by one. So if it's equal to 1, x must be equal to negative 14. But it's positive integer, so this obviously doesn't work. If it's 2, then it's negative 8. That also doesn't work. If it's 5, then it's 10. This works. If it's 7, then x is equal to 22. That also works. And then, of course, finally, it could be equal to x itself. And that would give x equals 4. So this together, if you add, is 36. Each region can be colored with one color. You can do red, orange, yellow, blue, green. So these are 5 colors. And then you can, so, okay, how many different colorings are possible? Then this can be colored with 5 colors. And then this adjacent square here can do like everything except this color, so it's 4. This one, the two of these are different, so these already cover 2 colors, and this one must be different, so it's 3 possibilities. And then with the same reasoning, this is 3 possibilities, and with the same reasoning, this is 3 possibilities. So you can just multiply them together and get 20 times 27, and that's 540. All right. This infinite product evaluates to a real number. What is this number? First instinct is to write in exponents. So this would be to 1/3, to 1/3 times 1/3, to 1/3 times 1/3 times 1/3. And then you can just put everything into one exponent. Oops. And you would see that this is a geometric series. And this would just be 10 to the 1/2. And that's root 10. On Halloween, 31 kids walked into the principal's office. Some are always true, some are, okay. Are you a truth teller? The principal gave a piece of candy to each of the 22 children who answered yes. Okay, so you have 3, yeah, okay. So we can list a chart. So let's call them group A, B, C, D. So these are the truth tellers. These are the false, the lie tellers. And then there are the alternating that start with truth, and there are the alternating that start with F. So we can simulate, or like we can figure out what their responses, the truth of their responses for each. So C would be true on first, false on second, true on third. D would be false on first, true on second, false on third. And then are you a truth teller? So who would answer yes to this? So the truth tellers would, the false tellers would, the true telling alternating teller would not say so, because they wouldn't say they're a truth teller. But the group D right now, who are basically liars, would say that they are. Are you an alternator? D would say yes. C would say no. B would say yes, right? So alternator. And T would say no. And then, are you a liar? T would say no. F would say, they would also say no. And the alternating true would say no. The alternating false would say yes. So it would look like this, I think. And so this would be 9. So group D is 9. And then 15, B is 6, and A is 7. So the answer should be how many pieces of candy in all did the principal give to children who tell the truth? 7 only, unfortunately.
All right, so next is a pairing question. Here we have 1 to 14, and they want to be arranged in 7 pairs so that each pair, the greater number is at least 2 times the smaller number. Let me write those out real quick. 12, 13, 14. We can look at this from the perspective of 14 first. 14 must be paired with something below 7. 13 must be paired with something below 6. 12 must be paired with something below 6. 11 must be paired with something below 5, and so on, until you get to 8. 8 can't pair with anything here, just like the other ones, and 8 must be paired with something less than or equal to 4. So 14, or actually 8, so if we start with this 8 over here, it has 4 choices. So let's say we chose a 2, and the 9 must choose something less than or equal to 4, so it's still the same boundary. And so this 8 had 4 choices. This 9 would have to choose from one of the 3 remaining choices of 1 to 4. So the 9 would choose another. So that would be another 3. This 10, so we already did this 9. This 10 can get anything from 1 to 5. So that would be 5 minus 2, we've already taken 2, and that's three choices. So we did the 10. And now with 11, we still get 1 to 5, but we've chosen one more. So we get 2 choices. For 12, we have 6 minus 4, so that's 2. And we can choose... so for 12, we can choose 2. And then 3, it's still 6, so we get 1 choice. And 14 has to be 7. So it's like this. And the answer is 12 squared. And that's 144. So for this next one, we can just put both logs together. So we have log 6 x over 9, absolute value, equals log 6 10 over 6, right? So the reason behind this is because log a over b is equal to log a minus log b, and the distance between two numbers is just the absolute value of their difference. So basically here we put 1 into log 6, we take their difference and we take the absolute value, that's their distance, right? So what we can do here is we can just take, so we can remove the, we can remove the absolute value here because this is greater than 0, and we can do some casework. So log 6 x over 9 is equal to log 6 10 over 6. So that's when whatever's inside is positive. If it's negative, then we just simply then the inside just must simply be equal to negative log 6 10 over 6. And we can just assign them, let's say, we can just solve each of them. I mean, that would be the fastest way. So log is a monotone function. X is equal to, then this is equal to this, right? And then we have x is 15, or we have x is equal to here. We would just reverse this. So this would become log 6 over 10. And we can put them together to get 54 over 10. And that is 27 over 5. And so if we multiply these two together, it would be 81. So answer is E. All right, so next problem. We have a midpoint on a tetrahedron. Tetrahedron is basically 4 vertices, 6 edges. It looks something like this. This is bird's eye view. And we have A, B, C, D, let's say. And we have the midpoint of ABM here, and we have CDM. And what we can do is we can consider the cross-section of CDM. So we have CDM. And the fastest way to just find this angle, CMD, is by knowing all the lengths. So we can assume that the side length of this regular tetrahedron, which means all the sides are the same, is 1. So CD is 1, AD is 1, DB is 1, and AB is 1. So now we can focus on ABD. So ABD is an equilateral triangle with side length 1. And we have essentially taken this midpoint M here, and we are interested in DM. And we notice that dm is equal to cm by symmetry, right? So we can find out what this dm is. This dm is root 3 over 2 after the Pythagorean theorem. So cm, dm are both root 3 over 2. And we can apply the law of cosines, right? So law of cosines gives us cd squared is equal to dm squared plus mc squared minus 2mc md cosine cmd, right? And then we can just plug everything in. 1 equals 3 over 2 plus 3 over 4 plus 3 over 4 minus 2 times 3 over 4 times cosine cmd. And we have negative 1/2. Negative 1/2 is equal to negative 2 3 over 4 cosine cmd. So cosine cmd is equal to 1 over 3. And that is our answer. So just a quick recap, we considered the cross-section CMD, we found all its sides, and used the law of cosines. Alright, R is the region in the complex plane of all complex Z that can be written as the sum of complex numbers Z1, Z2, where Z1 lies on a segment with endpoints 3 and 4i, and Z2 has a magnitude. Okay, so we know that. Let me find some space. We'll just do it here. So Z1 lies on this segment with endpoints 3 and 4i. Oops, that's very small. So, let me draw more. Real imaginary. And we have 3 and 4i. So 3, 4i. We can draw a little more. And so Z1 is essentially here. Z1 is somewhere here. And notice we can treat complex numbers like vectors, right? You can, when you add them, you're sort of getting their vector sum. Or like your, for example, like Z1 points here. Then Z2, you can keep on going with an arrow. And this Z2, we notice, is something within the unit circle, right? It is has magnitude at most 1. So Z2 is some complex number within this circle right over here. So for every point here, Z1, after we add a Z2, it would be essentially like we have a point here and we have a circle of radius 1 around it. And we can imagine dragging this ball around from 4i to 3. And so it would form this path that looks like this. And all the possible Z1 plus Z2 are within this area right over here. So what does this area, or what is this area equal to? And the way we can compute this is that we can notice, let me zoom in a little more. We see that here, from this point, the furthest point is perpendicular to this 4i3 line, right? And here, from this point, it's also perpendicular. And basically, every point you drag this to, the furthest point would be 1 away from this line. So it would form this rectangle with width 5 and height 2, right? So radius 1 plus 1. So this would be 2. And then on the two ends, the frontier is essentially formed by the point 4i and 3 themselves, right? So we have here this and this. And that would be, they two would together add to a circle with radius 1. So that would be pi. So the total area is 10 plus pi, and that is around 13. So for this next one, we can use a fairly classic trick, is to let a be log 2 and b be log 5. And we notice that a plus b would be equal to 1, as this is just log 10. And this is just b cubed. This is 1 plus a cubed, because log 20 is just log 10 plus log 2. And this is log 8 is log 2 cubed, so that's 3a. And log 0.25 is log 2 to the negative 2, so that's negative 2a. Combining the terms, we have that this is b cubed plus a cubed minus 3a squared plus 3a plus 1. We can substitute this b, right? So we can go b equals 1 minus a, and we can just essentially expand this out. So this b cubed term would give us a cubed negative a cubed plus 3a squared minus 3a plus 1. So after expanding, this new sum would become cross 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 2. Right. The roots of the polynomial this are the height, length, and width. A new rectangular box is formed by lengthening each by 2 units. So this is just Vietas. We would see that if we have x1, x2, x3 as solutions to this, then its original volume is or actually we don't care about its original volume at first. So if we have these as the dimensions, the new rectangular box would have volume x1 plus 2, x2 plus 2, x3 plus 2. And that would be x1, x2, x3 plus 2 times x1, x2 plus x2, x3 plus x1, x3 plus 4 times x1 plus x2 plus x3 plus 8. Now each of these terms we can find with Vietas on this polynomial, right? So or based on the fact that x1, x2, x3 are the roots to this, or are the zeros of this this polynomial. So we know from Vietas that their product is equal to 6 over 10. Their sum of pairs is 29 over 10, and that their sum is 39 over 10. And so this we can just plug in. We can just plug in everything. This would be 6 over 10 plus 2 times 29 over 10 plus 4 times 39 over 10 plus 80 over 10. And this would be 6 plus 58 plus 4 here, 6, 3, 1, 5, plus 80 over 10. And this would be 162. 162 over here, that would be 220, 300 over 10. So this is just D right over here. Right, so this next question asks us to find the fourth smallest triangular number that is also a perfect square. Now, we can write an expression for the nth triangular number. It is n times n plus 1 over 2, right? This is just this sum. And this should be some k squared. Now, the first thing we can notice is that this over 2 is very inconvenient to deal with. So we can first do a case where n is even. So if n is even, n over 2 is a whole number, and n plus 1 is an integer. So we have this, and we notice that these two do not share any factors. So their GCD equals 1. And this is because n and n plus 1 are 1 next to each other, so they too don't share any factors. And after you divide by 2, this is going to lose a factor, so there's even less chance of them sharing a factor. So these two do not share any factors, and they must be equal to k squared. This means that any prime inside of k would k squared. So let's say p to the e divides k squared, or like p to the 2e actually. So if p to the e divides k, and like e is the biggest exponent of p, and p to the 2e divides k squared, then this p to the 2e must go completely into n plus 1 or n over 2. Like one of these. So whatever prime you have that goes into this, all of that prime would go into n plus 1 or n over 2. And the conclusion here is that all of these are squares. So therefore both of these here are perfect squares that do not share any factor. So then we can just go and search for squares. So we notice that n over 2 is a square, while n plus 1 is also equal to a square. So n is 2 times a square, but then also it's 1 less than a square. So we can just go and list some squares. actually, let's list y squared and see if that square minus 1 is double of another square. So we can just go search and notice y we only need odd. So because if it's even, then it can't be, then it minus 1, y squared minus 1 cannot be even. So we have 1, 9. 9, notice, produces x equals 2, and that gives n equals 8, which is exactly what we have for T8. And that's a good sign that we're on the right track. So 9, 25, no. 49, no. 81, no. 121, no. 169, 225, 289. So 289 would give, minus 1 is 288. So n equals 288 would actually give x is equal to 12, right? So this is 2 times 144, which is a square. And we also can check that n plus 1, 289, and 144 do not share any factors, right? They do not share any factors, and they're both squares. So n equals 288 is a valid solution. And it is the smallest solution for the case where n is even. So then we can keep going with n odd. So this is a very similar case, and basically we can reach the same conclusion for these two. And we notice that here n is either a square or this is a square, which would give 2y squared minus 1. So then we can just list down all the odd x squared. So again, as we did here. And we can check if each of them is one less than double of another square. And after checking, we would notice that this 49 is actually corresponds exactly to this t49. So here, this is x squared, right? And n is equal to x squared. And this matches this and this being squares and coprime. So this works, but then it's already covered. And if you check the rest, here you would get to n is equal to 289, and you would realize there are no solutions here. And if you go on, these n's are all going to be greater than this. So the answer is just 228. And we want the sum of the digits of this, and so we just plug in 288 times 289 over 2, and that would give 144 times 289. That would be 6353 1156 289 over 6116114. So 41616, and we get 18. So D. All right. This next one, we have this equation that only has that has more than one solution in this interval. Well, first of all, we can try an algebraic method first. You could try to graph it, but then it's best if you first explore a little of the algebra behind it in case there's something. So sine x, we notice that there's a double angle formula here. So let me just 2 cosine x sine x. And then de Moivre's theorem would just give sine 3x is equal to the imaginary part of cosine x plus I sine x to the third. And if you take the imaginary part, that's just going to be sine cubed x minus negative sine cubed x plus 3 cosine squared x sine x. And after crossing the signs, we would have a times 1 plus 2 cosine x is equal to, and we want to write everything in terms of cosine. So we would get plus cosine squared x minus 1. Then we can write this, we can write y equals cosine x, and this would give us 4y squared, 4y squared minus 2ay minus 1 minus a, so this is minus 1 plus a, is equal to 0. Then we can just plug this into the quadratic formula and see what this gives for y. So y is equal to 2a plus minus 4a squared plus 16a plus 16, and this goes over 8. And then we notice that this is a perfect square, so we can write that out very nicely, like this. And we can figure out what each of these are. So if we take the negative sign, it would be 1/2. If we take the positive sign, it will be 4a plus 4. So that would be a plus 1 over 2. So we have these two solutions. And we notice because we have two solutions essentially, or like, so this y is a cosine x. So this is a cosine x. And our solution needs to be from 0 to theta. So this y should, in order for any y to be a valid solution, we need y to go within -1 to 1, right? It would correspond to a successful angle of x. And so here, this -1/2 works, and we want this a plus 1 over 2 to be within this range. So a plus 1 over 2 should be within here. And so a should be 1 between -3 to 1. Right, so this is our constraint for a in general. But then also we want more than one solution, and these two might overlap by chance, right? So we consider the case where they're equal, and that would give n is equal to -2. So a is not equal to -2 then, and this means that then our intervals would just be -3, -2, union -2, 1, and their sum would be -3, -2, 1 is -4. Right. Okay. Transformation in the coordinate plane, rotating k degrees, and then reflecting it across the y-axis. So one good thing to do here is just to simulate this, or like to look at what this would look like. So for an n, we would keep going. We want to find, essentially we would keep going, we would keep increasing our index until we get back to its 1, 0. Okay, so let's just see what happens. So let's say we start here with 1, 0. And we started by rotating by 1 degree. So let me label this as 1. It means 1 degree. Actually, let me just erase this real quick. Okay, so we're at 1 degree, and then we rotate this over the y-axis. All right, so this is 1 degree, so 1 degree from this axis, and then so this is after t1, so this is t1. T1 would get us at 1 degree. All right, then we can keep going. We would rotate this by 1 degree, so it would actually be exactly to the opposite of this first temporary position. And then we would rotate it over the y-axis again. So it would come here, right over here. So this is 1 still, and this is t2. So this is 1. Okay. Then we would rotate this by 3 degrees. So this temporary position would now be 2 degrees from the x-axis, and then we would reflect it over the y-axis like this. So t3 would end up here with 2 degrees, and then we can keep going. And we would notice that after the fourth temporary position would be 2 degrees from the negative y-axis. And after reflection, it would be 2 degrees here. So this is what happens after the fourth move. So we can just conjecture that this will go on and on and on until, let's say, we hit the y-axis. We'll see what happens when you get here. So this here would be T180, 177 would be 89 degrees. And then you would hit here, so this is, we keep going, T178 is 89 degrees, and then here we would get 179 degrees, T179 would get you to 90, or the positive y-axis, and T180 would get you right over here. So T180 would get you here. Okay, so now this is the key part. It's like we want to know what happens once it hits the y-axis. Maybe it just keeps going. So now we would go, okay, I'm going to rotate this by 180 degrees, counterclockwise, right? So here I'm going to go 181. I'm going to get here, and I rotate this over the y-axis. So it seems like this pattern can just continue. So the 181 falls here, and then if you do this again, you would end up here. So it just keeps going until you would hit the x-axis. So this 181 would keep going to hit until it hits the x-axis after 90 more steps of 2. So here it was 179, just a reminder, and you would keep taking 1 degree being a step of 2, so it would be plus 90 degrees each take 2 steps. So it would be 359, like this. All right, moving on. we want to know the number of ways to order the 13 factorial possible orderings of cards so that we can take them in 2 passes. So just a quick explanation. So here, first pass would take 1, 2, 3. Second pass would take 4, 5. Third pass would take 6. Fourth pass will take 7, 8, 9, 10. And last pass will take the rest. So basically, you can only go left to right and take strictly in order cards, starting from 1. So here we actually have 2 passes, and they need to take away everything from 1 to 13. So let me write down these numbers: 10, 11, 12, 13. And basically, what we can notice is that the first pass will take 1 to a certain number. So let's say it took 1 all the way to 9. And basically, by the time it finishes with 9, after that, it would get to the end, and then it would take the rest. So, for example, one possible way to do it would be, okay, I have this, and then like somehow 10 is here, maybe 11 is here, 12 is here, 13 is also here, 14 is here. Then this would be 2 passes. So then, in order to have this happen, we notice that 1 to 9 must appear strictly in this order, while 10 to 13 must also appear strictly to this order. Then the rest is pretty much random. You can do whatever you want, except one configuration. The only configuration you can't have is this thing itself. So this is the only configuration that you can't have. Anything else would definitely bring this 9 after this 10, right? So if you consider like any other configuration would put this 9 after this 10. So then for 9 here, the number of ways to do this. So if we put the cut here, then the number of ways to have this would be, out of the 13 positions, you choose 9, right? And so all of these positions would work as first pass take 9, second pass take the rest. Except the one where we have this exactly, right? And so basically this reasoning could work for any cut. So you can cut anywhere you want. So starting from 13, choose 1. You can go all the way to 13, choose 13. 13, choose 12. And this is essentially our answer. Answer. And so here, we notice that this. So if we collect all the 13 choose something, 13 choose 2, all the way to 13 choose 12, we notice that this is just simply, or actually let me finish collecting. So this is minus 12, so we got 12 ones. And then here, this is just 2 to the 23, to the 13, minus 2, right? So if we consider the identity of the nth row of the Pascal's triangle, it's just the sum is 2 to the 13, and then here we lack a choose 0 and choose 13, so it's minus 2 and minus 12. And so we can just calculate this. This is just this, and the answer would be D. All right, next one, we have an isosceles trapezoid ABCD. Let me just try drawing one. I'll draw it like this. All right. A, B, C, D. There's a point so that we have P. PA is 1, PB is 2, PC is 3, and PD is 4. Then we want BC over AD. So let me zoom into this diagram. It's actually fairly ugly. And we want BC over AD. We also know that these two sides are the same. It's an isosceles trapezoid. So the nice thing about isosceles trapezoids is that they're cyclic. So this would motivate us to leverage some of the symmetry and reflect B about the angle bisector of BC, or you can say the angle bisector of AD. So like if we have something like this, we can reflect this over this line here, and you can do all the connections to this point P prime. This is some very bad drawing. P prime. So we have P and we have P prime, and this P prime would inherit all the properties from P. So for example, because C is the reflection of B over this. So let me just draw this a little bit more clearly. This mirror line, and P prime is the mirror of P. Then BP is equal to CP prime. So this would be 2. BP prime is 3. AP prime is 4. P prime D is 1. So this has inherited all the properties about P, and and we also notice that BC P prime, so PP prime, and AD are parallel, right? They're all perpendicular to this mirror line, and so we would notice that BCP P prime and AP P prime D, so that's a mouthful, they are all isosceles trapezoids. And that gives them the property of being cyclic. And whenever we have cyclic, we can use Ptolemy's. And that turns out to be very powerful in this problem because we have BC times PP prime plus 2 times 2 is equal to 3 times 3. While on the other hand, we have AD times PP prime plus 1 times 1 is equal to 4 times 4. And we want BC over AD. So what we can do is after we move these to the other hand, so we have 5 and 15, we can just divide, and we have that BC over AD is 1 over 3. So the answer is B. So next, we notice that for a polynomial to divide p of x, all of its roots must also be those of p of x. So we're just going to quickly check for their roots. So this thing we can rewrite as x to the third plus 1 over x plus 1, or you can just solve the quadratic equation, right? So this is equal to 0, and you can solve for x, and then we can put this on the complex plane, and we notice that it corresponds to these three. We can apply our knowledge of roots of unity, and over x plus 1 would eliminate this branch, or like this solution. So we're left with these two, and so sampling the top one, we would get e to the I pi over 3. And so if we try to plug this in here, we would notice that essentially this is 1/6 of the whole circle, right? So this would take it 2022 times. So that would be, this is a multiple of 6, in fact. So it would take it back to here, right? So 1/6 of a circle, you take it 2022 times, and it would go back to 1. So this is 1 plus x to the 1011. That is going to be well, you're going to take 1/6 1011 times, and so this is just going to be well, this is 3 multiple of 3, right? So this is going to be something halves. So it's going to take it right to the opposite corner. So this is going to be -1, and this is going to be +1. So added together, this is 1, and so this root of a does not divide this. So this is eliminated. We can do the very same thing here. In fact, this is easier because it's x to the 3 minus 1 over x minus 1. So they're directly the third roots of unity. And we eliminate this one. So it's e to the I 2 pi over 3. And so this is 1/3 of a circle. So here you would take some multiple of 3/3 of a circle. So this would be some whole number of circles. So it's 1. Here it's also a multiple of 3. So +1 plus 1. This one's even worse. I just want to give it a 3. So this is also eliminated. Then for this one, you would see that one possible way to do this is to have e to the I pi over 4. Right? So one of the roots is this. And after you plug this in, this is essentially 1/8 of a circle. After you get 1/8 of a circle, this here would be, well, 2020 is not a multiple. 2016 is a multiple of 8. So you would go 6/8 of a circle, which is here. And then this here would take me 3/8 of a circle, I believe. Yeah, 3/8 of a circle, right? So this would be somewhere here. And so adding this, you would get this plus this, they cancel out, and +1 gives a 1. So this also does not divide p of x. Then here, this one, for this one we have we can just, again, roots of unity would give us, so this is x to the 9 plus 1 over x cubed plus 1. So the roots would look something like this. So we would get, this is -1, and we would get 1, 2, 3, 4, 1, 2, 3, 4. So these are the ninth roots of, actually they're the primitive 18th, but these are essentially the roots to this, and these must be eliminated. So like you take away these, and what you are left with are these roots. So taking one of them, this is actually just e to the I pi over 9, right? So this actually is 3 pi over 9. This is 5 pi, 7, 9, 11, 13, 15, 17, right? This would take us back. So here, this is a root of this, and we see that this is 1/18 of a circle. So if we multiply this to, let's say, 2022 and 1011, sorry, 1 over 18, then we would get something very messy, actually. So actually, let me do that here real quick. So 1, 1, 0, 2, 2, 1, 42, and this would give us 6 left. So this would give 1/3 of a circle. This here would give 1/3 of a circle. And 1011, when we take 1011, this would give us, so 2022 gives 1/3 of a circle. 1011 would give something even weirder. So 111 would give 6. No, it wouldn't get to a 6, right? It would. 6 would be a 108, and that's a 3. So this would give 1/6 of a circle. So adding them together, 1/6, 1/3 plus 1 would not give a 0. So this is also eliminated. And so here, you can check this again, but obviously there's only one answer left. All right, so this next one, we have two complex numbers satisfying this. So immediately Vietas would give x1, x2 is 10. x1 plus x2 is c. And you have these being the vertices of blah, blah, blah. But what's most notable is this, and it's that because these two multiply to 10, we know that they are complex conjugates. So z1 is, or z2 is the conjugate of z1. And because of that, we have z1, z conjugate of 1 is 10. And this means z1, the magnitude of z1 squared. So the magnitude of z1 is actually 10, root 10. And z2 is its conjugate. So what this would look like is z1 is something like this. It has length root 10. And z2 is its conjugate, or its reflection over the x-axis. Then furthermore, we can look at the other 2 points. So we notice that z1, the reciprocal of z1, is basically just the reflection of, so like it has an angle opposite to that of z1, right? Because 1 over z1 times z1 is 1, which means that the sum of the respective angles is 0. So 1 over z1 would actually share the ray with z2, so it would lie somewhere here. Let's say this is 1 over z1, and z2 would share a similar fate, so it would look something like this. So let me redraw the graph here real quick. This would look like z1 is here, then z2 is here. They are symmetric over the real axis. Oh, sorry, this was also real and imaginary. And z1, 1 over z1, we said it lies on z2 with 1 over root 10, the magnitude of z1, which is also the magnitude of z2. So if we were to actually have a measurement, so this would be 1 root 10 of z2 actually. So 1 over z1 is actually equal to this. And here we would similarly have 1 over z2 is equal to 1 over root 10 z1. So this is how it looks like, this actual quadrilateral. And its area needs to be maximized. And essentially what we have though is z2 is also the conjugate of z1. So like everything is based on this one point z1, and we can choose where its x value is. So like z1 plus z2, recall, is equal to c, but then it's also equal to twice the real part of z1, right? And so now we can let's first express the area of this quadrilateral, or actually this would be an isosceles trapezoid. It's actually just this big triangle, which is real z1 times imaginary z1 minus this smaller one, which is actually 1/10 the area of this bigger one. So we would just end up with something like this. So the area is actually something like this, which we want to maximize, right? We want to maximize this. And the way to maximize this, given that, so if we call this x and this y, we know that x squared plus y squared is equal to 10. Then the way to maximize this is clearly to give x is equal to y is equal to root 5, right? If we let both be equal to root 5, this xy is maximized. So then the real part of z1 is x. It is just root 5. So this is just 2 root 5. And root 5 is approximately 2 point something, and it is closest to a. Okay, so here we have the sum of reciprocals from the numbers 1 from 1 to n, right? So and after you calculate this, you can get a simplified fraction in this form. And we want to know how many of these is k of n, or the denominator, less than the LCM from 1 to n. So ln is the LCM from 1 to n. Now we can consider how we could get to LCMs naturally. So obviously, when you have a fraction like this, a sum of fractions like this, what you could do is you can convert. So let's call this L without the n. What you can do is you can convert the first one to L over L, the second one, 1 over 2, to L over 2 over L, all the way to L over n over L, and that would give you a shared denominator like this, right? So we can rewrite this into a summation like this. So these two, the left-hand side and this expression, are equivalent, and we want to know if this is simplifiable. So like if this expression here if we can simplify this, then that means we take a factor off of each, and the resulting k, would be less than L. On the other hand, if this is not simplifiable, or they are already coprime, then this k of n would still be this L. So in other words, we're trying to know for how many integers is the numerator coprime to the denominator. And that is essentially what we're trying to look at. Now, we notice that the LCM can only have the primes that occur from 2 to 22. So there are not many primes to consider. And basically what we can do is for each, we can sort of list a table, and we're going to consider for each prime if they both have the same exponent of that prime. So we're going to start with we're first gonna deal with some of the easier ones, so then we don't have to deal with a lot of the small pesky cases. So when n is equal to 1, we have 1 over 1. So this does not work, as L is equal to k. For n equals 2, we have 3 over 2. This does not work. N equals 3, we have 11 over 6. No. N equals 4, that would be 22 plus 3 over 12, that's 25 over 12, no. N equals 5 would give us 60, right? So 60, 12 plus right over 125, and that's 137 over 60. That's right, right? Yeah. And then n equals 6 would give us 10 plus 60 plus 10 over 60 plus 137 over 60, so that's 147 over 60. And this is simplifiable, so we can divide a 7 on both to get this. So apparently 6 does work. So we're going to start working from n equals 6. So here, from 1 to 5, we don't have any that are true. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And we have p equals 2 here. So basically, for each of these primes, actually, let me list them all. P equals 3, 5, 7, 11, 13, 17, and 19. So for each of these primes, we know that as long as the number, or like this n here, as long as n is greater or equal to p, then L will contain p. So p divides L. So which means that all that's left for us to check is if p divides this thing right over here, which we'll call S of n. If p divides S of n, and this is what we're gonna check for in here. So as long as you have one checkbox, so let's say 9 has a checkbox at 2, that means that you are that means that you share some factor. So these two share a factor, and this is not true. So basically, as long as you have a tick in the column, then this whole number goes no. All right. This is what we're gonna do right over here. Now, for this 2 right over here, we notice that the LCM, this LCM contains, for 6 and 7, they contain 2 copies of 2. And the only way to completely exterminate that is with a 4. So if you have L over 4, then you would exterminate it. And this would only occur for one of them, right? So each term here contains a factor of 2 except this factor. And for that factor, for that term, it would be odd, while all the others are even. So for 6 and 7, we do not see a factor of 2 in S of n. For 8, once 8 comes, the L has 3 copies of 2. But then again, 8 is the only one capable of eliminating the factor of 2 completely from L. So again, you would have one odd term with a bunch of even terms. So for 8, 9, 10, 11, 12, 13, 14, 15, this would always be the case. And then here for 16, you would notice this happens again. So 16 makes L have 4 copies of 2, and the only way to eliminate that is through an over 16. So all of these here would be gone. So none of the 2 doesn't help us with anything. All right. So now on to 3. For 6, 7, 8, L has 1 copy of 3. So L has 1 copy of 3. And only for 6, 7, and 8, only 6 and 3 are capable of eliminating something. So what we can consider is, so this S of n, this S of n is equal to, or actually we're just going to use congruent to, is congruent to L over 3 plus L over 6. Notice that all the other terms have a factor of 3 in them, so we can just eliminate those. So we have this plus this mod 3. And then we notice we can just simply write this, because they're both integers, we can just write this as L over 2. But then L contains a factor of 3 and has the factor 2 in it, obviously. Then this would just have a factor of 3 in it. So this would be congruent to 0. So for 6, 7, and 8, we have that this is true. So like we have all of these. When 9 comes, L would have 2 copies of 3, and the only way to eliminate that is by having a 9. And so all of these would again would have one factor that does not contain a 3, and all others that contain 3s. So none of these here have a factor of 3 in them. Have 3 divides S of n. Then when 18 comes, the story could change a little bit, and we're going to check. So now there are two numbers that are capable of eliminating the factor of 3. And so we have L over 9 plus L over 18. And we can, again, we're considering mod 3, right? And here we can simplify this into L over 6, but then L has two factors of 3. And so this would have a factor of 3 in it. So this is 0. This means that in this case, 3 divides S of n, and this we can say for everything here, which means here we already have 8 candidate answers, and so like we're already in a 2 choose 1 situation, and so we can keep checking for 5. So let's look at 5 now. For 5, for everyone, we can make the same argument, right? Because for 5, we know that L for all of these numbers would only have one copy of 5. And so for each interval, we can go and check if this happens. So like for 6 to 9, obviously you can't, oops, let me get back here. You can't have anyone that works. And then for once 10 comes in, you essentially have two terms that can possibly eliminate the 5s. And that would look something like this. And what we would end up getting is a 3L over 10. And this would still not have a factor in there, because this is not congruent to 0 mod 5. Because again, the 5s are eliminated. So here, none of these work. And later you would add another 15, and then you can add this. This is 30. This is 2L plus 9L. So this is 11L over 30. And we still see the factor of 5 being removed from L. And then here, plus L over 20, and that still doesn't help. So you can see this is 3L plus 22L, and that's 25L over, oh, this did help then. 22, but it doesn't really matter because they already have ticks on them, right? So apparently these are also ticks. Then for 7, you can go through the same reasoning. So for 6, 6 wouldn't be concerned with this at all. So like as mentioned, you want the n to be greater or equal to p. Otherwise, it's this 7 does not fit into L at all. So we don't need to consider this. And then for 7, you can make the argument for like only one being valid. So you just go like this, until you reach 14. And then you can go again with L over 7, L over 14. This is equal to 3L over 14. And so obviously this still doesn't work. And then this we can just ignore because they already got ticks on them. And then 11, these would all be irrelevant. And then you could just go all the way here with the same argument. And then 22, we wouldn't bother to care. And then here for 13, again, nothing works. And then nothing works here, and then nothing works here. So the answers are just these 6, 7, 8, 18, 19, 20, 21, 22. So the answer is 8. And I would say this is actually not that difficult to think of. It's a little bit brute force-ish, but then it's also very fast actually. This is not a very difficult one to think of. All right, this next one. For this one, I'm gonna show a brute force approach. I'm just gonna go through all the cases, but it's gonna be very organized casework. That's probably the thing that you should learn from. Otherwise, there is something that they overlooked when they made this problem, I think, and it is that there's only one case. So like before, like the general approach to this is you could first decide, so for the digits 0, 1, 2, 3, 4, you can first decide how many of each you want to take. And you would realize there's this one case where you can take, so actually let me just quickly restate the problem. So like you have at least one where the digit is less than 1, or it's less than or equal to 0. So it's equal to 0. You have at least, wait, what am I doing? You have at least one that has 0, you have at least 2 that are in 0, 1, you have at least 3 that are in 0, 1, 2, and you have at least 4 that are in 0, 1, 2, 3, 4. 1, 2, 3. And there is this one case where you can choose 5 zeros and 0 of others. And this is something that you can't do for any other number. So for example, if you wanted to do this on 1, you would violate the first one, right? So because you would always need at least 1 for the 0. And you would realize that this here would give you one situation, right? But then for all the other ones, you would have at least 2 digits that are non-zero. So for example, you would have 2, 3, you would have 1, 1, 1, 1, 1, you would have 1, 1, 2, 1, 0. And they would all, the number of ways you can permutate them. So like, for example, with this 1, 1, 1, you're taking one of this, one of this, one of this, one of this, one of this. That would give you 240 possibilities. And so you would realize that whenever you don't have everything piled on 1, you would get a factor of 5 in the number of possibilities, which means that the answer, because there's only this one unique case that gives 1, would be a 5k plus 1. So if you just look at the answer choices, the only one that satisfies it is E. And so we're done, technically, if you looked at the answers carefully. But we're going to go through a brute force approach. But if you're satisfied with this answer, you can just skip ahead. And so what we have is, so we're going to do a 0 column, a 0 row, so we know that this needs, up to this point, we need at least one person, or one digit. Up to 1, you need at least 2. Up to 2, you need at least 3. Up to 3, you need at least 4, and up to 4 there are no restrictions. All right, so now we're going to start brute forcing. So we're going to start with the case where things are nicest. Nice being like how far you are from violating a condition. So here obviously you can't violate anything. So total number is 1. When you have a 4 here, you can put a 1 in any of these places. And so there are 4 situations, and in each situation you would have a 5, right? So like you would have one unique element, and you would choose a spot in the 5 digits. Then when this is 3, you can pretty much do anything except put a 2 here and 0 on everything else, because you need at least something here. So actually we can still do a little casework here. So basically you can double on each of these. That would give you a 5 choose 2, that's a 10 for each case. That's 3 times 10. Or you could choose to put a 1 here and 1 here. And you would realize that you can do this for all 6. Because if you have 1 here, you would at least have 1 somewhere else. So this would be 6 times 1, 1, so it would be 20. Now then you have a 2 here. This is another case. When you have a 2 here, pretty much you don't have to worry about this. But actually we can just keep doing casework. So we go with a 3 here. If we have a 3 here, this is just a 10, right? Yeah. If you have a 2 here, you pretty much don't have to worry about any other restriction. You put a 1 here, put a 1 here, put a 1 here. That's going to give you 5 times 6. That's going to be 30 each for 3 times. If you have a 1 here, as long as you don't put both here, you're good. So we can still do the same thing as before. You can put 2 here, 2 here. That's going to give you 30 times 2. Or you can choose to put 1 here, you can choose 2 of the 3 remaining ones and put 1 of each there. So you can have a 1, 1 like this. These would give you 60 each, and they can happen 3 times. And then finally, you can choose not to put anything here. And then the show goes on. So you could choose to put a 3 here. That would give you 10. You could choose to put a 2 here, 2 at 2. And then that allows you to do anything you want later. So that's going to be 30 each for 2 times. And then you can choose to put a 1 here. And then if you have a 1 here, you can choose for the later one, you can choose to do this or this, but you must still have at least 1 at the 3 point. So you would get one of 30, and you would get 1 of 60. where basically you get 1112 or 2012, right? Like this. Right, so that is, can you choose a 0 here? No, because if you have a 0 here, then across the total 3 here, you would have less than 3. So that's not valid. And then we move to the final case. So you have 1 here. You can choose to put all 4 here, right? That would give you 5. You can choose to put a 3 here. And then once you have that 3, you can do whatever you want with the last one. That's going to be 3 times 20. You can choose to put a 2 here. If you put a 2, then you got 2 left, and the only thing you can't do is put them both here. So again, you would get this. So these would each give you 30 for 2 times. You could do this. So that would be 60 for 3 times. And then you can have a 1. If you have a 1, then this is also the last case. So like you can't have a 0 anymore. So you would get a 1. If you have a 1 here, you could put all 3 here. That's a 60. You could put a 2 here. If you put a 2 here, then you can do whatever you want with the other one. So you could do this. That's going to be, oh, sorry, this is not 60. This is 20. And each of these would give you a 60, I believe. So if you put a 1 here or a 1 here, these would be 60 times 2. Oops, let me keep it uniform. And then finally, if you have a 1 here, which is the smallest, which is the worst you can do, you can choose to have a 1 here. You can choose to have a 2 here, which would give you 60, or you can choose to have a 1 here, and a 1 here, I believe. Yeah, you can't have both here. So you can't have a 2, 0. That wouldn't work. So this last case would give you 5 factorial, which is 120. Right. And then we can just add them up, right? That was a huge casework. That was very big. So 1, again, this 1 that gave it away, 20 here. Here you would get a 150. Across these two, you get 100. Here you would get a 60 plus this, so it's 240. This is a 70. This is a 5. So this is a 95. This is a 60. This is a 60 plus, so 240. Here, these together gives you a 200, and this gives you a 120. And then adding these together, you get 271. These are 310. This is 300, 500, 620, and this is a 95. And then adding these together, we have, so these two nicer ones would give 930, and then these two would give 366 to ultimately reach the desired answer. So that was a hell lot of casework right over here, though. All right, final problem. Here we have a circle with a certain radius, and we want to know, so we have integer points, this and this, that are tangent to the circle. And we want to know some information about two of these, two extreme solutions to this. So let me draw the configuration here. So we have the x and y axes. We have a circle. It's very difficult to draw. So you have r here, and you have r. And basically a successful configuration could look like this. Oops, what have I done? It could look something like this, where it would hit the x-axis at A and the y-axis at B. And another configuration, actually a very subtle one, is to hit it right over here. This would also be valid. And so we're going to summarize some equations that we can derive from these. So first of all these equations are between A, B, C, and R. And so one thing that we can derive very obviously is the Pythagorean theorem. So this is evident. Another thing that's not so evident, so for this blue case, we would see that the two tangents from a point to a circle are the same. This length can be represented by a minus r, and so this is a minus r. With the same argument, we can do this is b minus r. So their sum is c. This is the other thing that we can get for blue. For red, we see that since this is beneath, this tangent here is actually equal to this, which is r minus a. So r minus a plus r minus b should be equal to c, which is the exact opposite of the previous one. So negative a minus b plus 2r is c. So we essentially have an or right over here. So they're actually very similar cases. And what we can do is we notice that since here we have a c squared, we can substitute them into this. And we would obtain something like this. A squared plus b squared equals a plus b minus 2r squared. And now notice, anything that we solve from this, so if we end up solving an a positive integer b, c, and r, that means that we are guaranteed to have a solution here, right? So if a plus b minus 2r is greater than 0, because they're all integers, and this is also an integer. So if this is an integer greater than 0, then we would get a valid c here. If this ends up being less than 0, then this here is true. We get a successful case here. And if this is equal to 0, this can't really be equal to 0, because if this is equal to 0, it's going to be a completely degenerate case. It would force a equal to 0, b equals to 0. So as long as we ensure that a and b are positive integers, this case won't happen. So each solution here to this equation corresponds to a valid solution right over here. So all we have to do is find an r. And so if we rewrite this a little bit, we would see that this is ab minus 2ar minus 2br plus 2r squared, and this is going to be equal to 0. And so we have a minus 2r times b minus 2r is equal to 2r squared, right? And so here we notice that this equation, if you're familiar with Simon's favorite factoring trick, which is exactly what we did here, then we would know that this actually has a lot of solutions. And in general, though, for these, we have the following restrictions. So we want to be greater than 0. We want b to be greater than 0. And there a, b, r. Also, they're all positive integers. That's what I'm trying to say. So a, b, r are positive integers. All right. Then SFFT, so as I said, Simon's favorite factoring trick has, whenever you get an equation, it has a lot of solutions. So here we should be confident enough, or brave enough at least, to try some r's. So we start with r equals 1. So we have a minus 2, b minus 2 is 2. And 2 here at most has plus minus 1, plus minus 2 as factor pairs as factors for the first. That would give 4 solutions. We want 14. That's way below than enough. R equals 2 would give a minus 4, b minus 4 equals 8. That would give plus minus 1, 2, 4, 8. So that's 8 possible factor pairs. This is also not enough. For r equals 3, we would get 2r squared is 18. That would give plus minus 1, 2, 3, 6, 9, 18. So that's 12 factor pairs, not enough. R equals 4, we would get a 32, and you get plus minus 1, 2, 4, 8, 16, 32. That is still 12 factor pairs, not enough. R equals 5 would give you 50, and that would be plus minus 1, 2, 5, 10, 25, 50. This is still 12 factor pairs, not enough. For r equals 6, though, things are going to change because 6 itself already has a lot of factors. It's a very nice number. We would get a minus 12. B minus 12 is 72. And so 72 is full of factor pairs. And so we can just check if this works right over here. So 72, 1, all the way to 172. Notice these would all give positive AB integers, and r equals 6 already ensures the other condition. So all of these here work very nicely. On the other hand, for negatives, notice don't forget the negatives for Simon's favorite factoring trick. You could get negative a. So for example, here for negative 72, we get a equals negative 60. That's not good. So this is eliminated. And you realize that everything would be eliminated until this, right? So you get like negative 24, negative 18, negative 32, etc. They would all not be good because they're going to get, even negative 12 gives a equals 0. And then negative 9 comes along with 8. This would give 3 and 20 for AB. And in fact, this is like one of these cases. So that is one of them for B. Oh, sorry, for negative A's. So this is 4. Negative 8, negative 9 would give 4, 3. So these two would work. And then everything here goes back to not being valid. So we have 2 here and 12 here. 12 comes from 2 to the 3, 3 to the 2. This gives 4 times 3 equals 12 factors. So here we get 2 plus 4, 12 is 14 factors as solutions as desired. And now we want to know what the ratio between the largest hypotenuse to the smallest hypotenuse is, or at least they're one of the largest and smallest. So let me continue right over here to note that the largest obviously occurs outside. It can't be down here. And something very nice is that usually the ones with greater differences, or like with one extremum, or like not extremum, like one extreme, is usually the one with the longer hypotenuse. So here, if we look for the largest A or B, we would notice that it is obviously with the 72 scenario. So A equals 84, B equals 13. So this would be the extreme long, and this would give C equals 85, and that is because you would realize you can do this fairly quickly actually, because you have this. But then for the small one, it's obviously one of these, and notice A and B are symmetric here. So it's really the same thing. So you get A equals 3, B equals 4, and that would give C equals 5. And so if you take their ratio, it's going to be 17, and we're done. So this is 17 right over here. So as we're nearing the AMCs, we've actually only got a couple weeks left. I might be able to have time to do 1 or 2 more. Please tell me in the comments if you want to see me do another. But later, after the AMCs, it's probably going to be Amy's. But I might keep doing these. Right. Thank you.